as in the ones that do like chemicals and science.
He did it like a lab, not a school, like what I did. But,
Like a proper
lab, yeah. I was like, we should say that, wasn't it? But now it's what you're going to be. You did it to us.
Okay.
Hey.
So we're moving towards the fundamental theorem.
Oh,
Finite abelian groups. Oh no, the focus. Hang on. Focus I can do.
It's right, really big, it's fine.
No. Actions.
Hey.
So this says, okay, I won't bother writing. We'll save time. You can see in 13.4. So any finite abelian group can be written as a direct product of these cyclic groups. And we can arrange it, as it's written there in the thing, we can arrange it that each of the cyclic groups has got prime power order. Okay, that's the thing we're moving towards. So we start with lemma 13.6. So the logic towards this is split up into a number of different steps. So this is the first one. And you should definitely hold Lagrange's theorem in mind as we discussed yesterday. Okay. So we let G be a finite abelian group. And we've got of order n, so we have the order of G equals n. And we assume that prime P divides n. So you've got P dividing n. The conclusion is G contains an element of order P. So within the group capital G, somewhere there is an element of order P, or an alternative way to think about that is G contains a cyclic subgroup. Cyclic subgroup of order P. Yeah, so if you got an element of order P, look at the cyclic subgroup generated by that element. You just get all the powers of that element until it returns to the identity. So it's going to be P different elements. Is that big enough for everybody? Yeah. That'd be clear. Okay. So the proof of this, okay? So we just took a 1 minute glance at it yesterday. So we can do this using induction in a nice, clever way. So it's going to be proof using strong induction. Remember strong induction? The normal, regular induction is where, like, you do your base case, and then you assume it's true for one number k, and then you prove it's true for k plus 1. Strong induction is where instead you assume it's true for every case strictly less than k, say, and then you use all those assumptions to then prove that it must be true for the next one. Yeah. Okay, so that's what we're going to do. And hi, George. Yeah. So we're just starting the proof of lemma 13.6. So first of all, we can look at a base case, just because it's quite easy to do it. So, i.e., G being the trivial group. Okay. It has order 1, but there are no primes P. There are no primes P such that P divides 1. So literally nothing to prove. Okay. Okay. So now we assume the theorem is true. Assume the theorem is true for all groups G with any order K. The order of G is K, where k is strictly less than n. Okay. Yeah.
It's funny, a silly remark. Where you put there are no primes, P, and then you put P divides 1.
Yeah.
Shouldn't that have a slash through it?
Well, yeah, so I'm saying there's no primes P such that kind of. So there are no primes P such that this holds.
Right.
Yeah.
Right.
Or you can say for every prime P, P does not divide 1.
Yeah.
Yeah.
Okay.
There are no primes P that have the property that P divides 1. Yeah. Okay. So we've made that assumption, and so now we give ourselves, so now let G be a finite abelian group of order n. Right? So we're assuming it's true, so n is some number, some positive integer. We're assuming the theorem holds for every case strictly before n. And at various points in the following argument, we're going to go back and use some of these assumptions. Okay? So in the following argument now, anywhere that we encounter a smaller finite abelian group, one that's smaller than G, we'll immediately know it has an element. When that's smaller than G and that some prime divides its order, we'll immediately now know that it has an element of that prime order. Okay? Because we've assumed it is so. Okay. Okay. So an easy case we can deal with first. Okay. So this has to be handled quite delicately because it's quite, all we know about G is it's finite abelian group of order n. And we're also assumed that P divides n. But some prime P dividing the size of n. Now the easiest case to deal with, because we've assumed very little about G. So that can make it difficult to make any progress. If you haven't assumed much about G, there's nothing to hold on to. You can't start talking about G because you haven't assumed much about it. Okay? So we have to kind of consider extra conditions that G might have. Okay? So the first of these is assume G has no non-trivial proper subgroups. So it's a group with, we're assuming, we're imagining, suppose G is very, very simple in the non-technical sense. There isn't much structure in it, so there's no subgroups in it. G is a group itself. Of course, it has the trivial group as a subgroup, and it has the whole of G as a subgroup. But we assume there's nothing in between. There are no genuine subgroups in G. Okay? Well, in that case, that means, well, if it's got no subgroups, then if you take any element, take any non-identity element, and consider the cyclic subgroup generated by that element. Okay. Now that construction still holds. This is still a subgroup, G. Consider all the powers of this G. It's a subgroup of G, but we've just assumed that G has no proper non-trivial subgroups. So this can't be some kind of middling intermediate subgroup. It must now immediately be the whole of G. As if we've assumed that there are no intermediate subgroups inside of G. Well, this is one we're trying, this is a subgroup now we're trying to talk about. It's not the trivial subgroup because it's a non-identity element. So inside here, there's at least the identity in G. So the only other subgroup it could be under this assumption is all of G. Okay? So that implies that G equals G by assumption, by the above assumption. And G has order n. Little g has order n.
there no shorthand for how to follow that?
Yeah, there is. So, well, some books use modulus, some books use a function like O, a function of, but I think, what has Jan been using? I think Jan encountered it first when he was looking at cyclic groups. But yeah, you can write the order of, yeah, so the modulus of the group element refers to its order. Or you can write little OG, O for order. Yeah. Okay, so G has order n, and so G has no proper subgroups, because G, the cyclic subgroup generated by G is now all of G. So this has no proper subgroups. But previously, in chapter cyclic groups, chapter 3, chapter 4, chapter 4 on cyclic groups, we saw that if D divided the order of G, then this thing, the cyclic subgroup generated by G to the power of D, was a cyclic subgroup of the cyclic subgroup generated by G, and this had of order the order of G divided by D. So cyclic subgroups are things that we can easily point to lots of their subgroups. If you take the generator, and instead of taking powers of the generator, you instead look at a divisor of the order and then take powers of that. So this will be all the powers of G to the power D. That will generate a smaller cyclic subgroup within the original one, and it will have order n over D, where n was the order of G. But our assumption that's in hold at the moment says that G has no proper subgroups. But this is a theorem that says it does. For every divisor of it, it has a subgroup of that order. So what's our conclusion from that? Or
There are no divisors.
yeah, there are no divisors, which I think is kind of what you were getting to.
Oh.
That the only, so there are no divisors. There are no genuine proper divisors of the order G. Because if they were, this thing from chapter 4 says, well, then you've immediately got a slightly smaller cyclic subgroup within this one. But we've imposed an extra assumption now that says there are no proper subgroups of it. So a consequence of that assumption then is, therefore, there are no Ds with D dividing n, except for 1 and n, which would give rise to just the cyclic subgroup itself. Or if you chose G to the n, well, then you'd be talking about the identity element, and that would be the trivial subgroup. So that means, so what type of number is n now?
Prime.
It's prime, yeah, because it only has divisors 1 and n. Okay? So n is prime, i.e. n is equal to p. P, remember at the very top, we assume p is a prime divisor of n. So in this, maybe not easiest case, in this initial case, where we make an extra assumption that G is kind of boring, there's no non-trivial subgroups, therefore it must be a cyclic group of prime order. So therefore this G is our element of order P that the lemma is asking for. Yeah. This little g that we've identified, it generates a cyclic subgroup that is all of capital G, So little g is order n, but we've just concluded now that in this case, n is the prime number. So little g is the element, you know, that the lemma talks about. Okay. So we proved it in that case. And that allows us to make progress, okay? Okay, we proved it for some kinds of groups. So you immediately ask, well, what about all the other groups? Well, for tackling all the other groups, those are the ones that don't satisfy this assumption. So that means we get an extra assumption about all the other groups. All the other groups are the groups that do have at least one or some intermediate, you know, some nice subgroups, some genuine subgroups that aren't just the trivial subgroup just containing the identity, aren't just the whole of the group, but just some genuine intermediate subgroups. Okay. So the lemma is true in this case. Okay. Okay. Any question about that? That sound reasonable? Yeah. So now, for the rest, we gain an extra assumption. We gain extra information. G has a subgroup of intermediate order. Yeah. Not the trivial subgroup, not all of G itself, but some genuine. So we have a H being a subgroup, genuine subgroup of G, and it has some non-trivial order, but it's not all of G. Yeah. So this is extra ammunition for us for proving the rest of the cases. Now remember, this is order n, and we've got this assumption that there's a prime number dividing n. Okay. Now remember, from Lagrange's theorem, not something we're not so much. Yeah, I think it's something we're using here. Kind of. The order of the subgroup is a divisor of n. And in fact, we get this nice factorization that n, which is the order of G, we can write it as a product. It's the order of G multiplied by something. And when you multiply, what's the number of cosets of H in G, isn't it? Remember the proof of Lagrange's theorem? We partition G by subsets of H. Each of the cells in the partition have the same number of elements, the number of elements in H. So the complementary factor here that completes this product is the number of cosets. But that's something we know as it's the size of the factor G mod H. Because this consists of all the cosets of H and G. Remember, just to bracket, because everything is abelian, only talking about abelian groups here, so H normal in G. Yeah? H is normal in G because these things are all abelian. And P is dividing n. Yeah? So conclusion, what does that tell us? P divides n.
Divides one of those two.
It divides one of those two. It's the quintessential thing about prime numbers. If a prime number divides the product, it can only do that by dividing one of the factors. Okay? You can't split up P and put a bit of it in here and a bit of it in here because it's a prime number. Okay? So that implies P divides the size of H, or P divides the size of G mod H. And that immediately gives us a structure for how to proceed. Okay. Remember, we're now in the case we've dealt with all the boring groups that don't have genuine subgroups. So now we're assuming the group has at least one genuine subgroup. But with just a little application of this basic fact about prime numbers, we're now telling us we've got two cases. Either P divides the size of H, or P divides the size of that. And these are extra bits of information we're getting. We can't say it's definitely this or it's definitely that. We don't know. We know it's just one of them. But we can provide an argument for each case. Yeah. So if we can successfully get to the conclusion of the lemma in this case, with some kind of argument, and then separately argue for the conclusions of the lemma in this case, then we'll have covered all cases, because we know either P divides this or P divides this. So that will finish our proof. Okay. Dealt with a kind of relatively straightforward case, the boring groups. These are the interesting groups, and one of these two things is true. Okay. So, one of these is true. They could both be true. At least one of these is true. So these are extra assumptions we can add to our list of assumptions, ammunition, to build our arguments. So firstly, we'll assume P divides the size of H. Now, what can we do in that case? Where are we? Well, yeah. Mathematically, where are we? We're in the middle of a proof. What kind of proof? By induction. We're in the middle of a proof by induction. Yeah, it was the very first thing we said in the proof. We will use induction. And so what was the thing we quickly dealt with the base case. And then here, we made the induction assumption. We said, okay, so now we're going to tackle a group of size n. But we tackle it armed with the assumption that the result of the lemma is true for all smaller groups. That's the nature of induction. You assume it's true for all the small things and use that assumption to prove it for the next biggest thing. And if you can do that in general, then you know it's true for everything of every size. Well, we're encountering the ability to use that assumption now. Because H is a smaller group. And here's a prime number dividing it. So we can just immediately use the induction assumption. Yeah. So by the induction assumption, second line, was it? Second or third line? By the induction assumption, that the lemma is true for this group H. The lemma is true for H. The lemma is true for H. So H contains an element of order P. And therefore G does. Okay? H is some amount of G. Yeah? So the element of order P inside H, it also lives inside G. Because H is a cyclic of G. Okay? So the lemma is true for G. Well, that's nice. Yeah? Just immediately it came out. But it isn't necessarily the case that P divides H. Could be. But if it isn't, we know it must be this one. Yeah. So now we can build another argument, but now armed with this. So secondly, or it should be like on the other hand, secondly, assume P divides size of G, size of H. Do we need to assume it doesn't divide? Yeah. I mean, if P divides H, then P divides the size of H, we can do that argument there, just using the induction assumption. So now we assume it doesn't divide H. So we're forced to assume that P divides the size of the factor group. I've done two orders, but that's the same anyway. Let's say the order of the factor group or the quotient of the orders of the individual group, that's the same thing. didn't mean to write that. I meant to write that, but it's the same thing. Okay. But now, but we can immediately use the induction assumption, okay? Because G mod H, note, G mod H is a finite abelian group of order strictly less than n. So the induction assumption holds. Okay? But it has an element of order p. Now, it's not so straightforward as in the previous case, where the element in H of order p was an element of G of order p. Okay, well, now we know there's an element of the factor group of order p. Now this means there's a coset of H, G that has order p. But we're not yet looking at an individual element of G. So, i.e., there exists, so there's a coset of H, so there's something of the form GH in the factor group. And the order of, now this is one case where you may be using those modulus signs for the group order of group elements might be slightly confusing. So that's why I'm writing out initially the order of G mod this coset is P. Sorry, is P. Because we're applying the lemma. We assumed the induction hypothesis that the lemma was true for all smaller groups. Okay. So there's our element of order P. But now we want to zero in, we want to find an element of G of order P. So we need to do a little bit of work. Okay, it's tempting to think that this element, little g, is the element of order P, but that's not true in general. Okay. But out of this element, little g, we can build our element of order P. Is everybody okay where we've got to?
Seems eerily similar to the number theory proof of if A divides P and B, where A and B divides P. If it's true for one, then stop. But if it's not true for one, prove for the other.
That was that was proving Euclid's theorem. That if P divided a product A times B, which is what we've used here.
Yeah.
That P divides this product, therefore it must divide one of the sum. Yes, no, you're exactly right. So well, what if it divided the first one?
Then you just stop.
Well, in the proof of Euclid's theorem, we stopped. Yeah. Here we build a little argument on that.
Yeah.
But then otherwise, you assume it doesn't, and you go and build another argument.
Yeah.
Yeah. So no, you're exactly right. It's following the same kind of flow.
Yeah.
Yeah. But so what can we do? Here's our coset of order P. So let's just write that out. I.e., if you take GH, raise it to the power P, you get the identity. What's the identity? The identity is H, isn't it? Because it's the identity of the factor name.
Yeah.
Yeah. But that's the same. Now, what is a coset raised to a power? Well, it's the coset represented by the representative raised to that power. Yeah. So that's the same as H. So but if this means, that implies that G to the power P is an element of H. Okay? Because if the coset represented by this element, G to the power P, the coset of H generated by that element is equal to H, that means that must be an element within H. Because if it was something external to H, this coset couldn't be H, because it would contain elements that aren't in H. Yeah. But we also know a little bit more. G itself cannot be in H, because this is a coset of order P, the prime number bigger than 1. So this is not the identity element in the factor group. So this coset is not G.
Only existing in G.
Yeah. So GH is not H, not the identity element. This is a non-identity element from the factor group. So the representative G is not in H. And now we need to really exploit information about the orders. We've got two elements of interest here, this element G to the P, and this element G. So what we do is we let the order of H, we want to name the order of H, let the order of H be R, and remember, P does not divide R. That was an extra assumption we got. We've already dealt with the cases where P does divide the order. We're now in the case where P does not divide the order. Well, P is a prime number, so if it doesn't divide R, it means the GCD of this pair is 1. And what you immediately get something that you can build with when you're looking at a coprime pair. If you're trying to build an argument around numbers and divisibility and so on, if you're looking at a coprime pair, it means you immediately know that there exists a linear combination of them equal. Exist integers s and t such that sp plus tr is 1. Okay? Being coprime to one another, being a coprime pair is exactly the same as having a linear combination equal to 1. Now, what are we going to look at here? Take our element, G to the P, raise it to the power R. What can we say that is? G to the P is an element of the subgroup H, an element of the group H, and we're raising it to the power R.
Is it simply just G to the PR?
Well, yeah, it is. Yeah, that's just rules of indices.
Yeah.
So yeah, so it is G to the PR, and we can also swap the positions. It's G to the R to the P. But all of them are a particular group element. There's only one answer to that. The identity. Yeah. So we know that because we're taking in that, so ignore the fact that it's G, some special G to some power P, but it's just a group element from H raised to the power R, where R is the size of H. Yeah. When you take an element and raise it to the power, the size of the group, that must give you the identity from Lagrange's theorem. Okay. Because as a way of looking at Lagrange's theorem, it tells you that the order of any element divides the order of the group. Okay. So if you raise any element to the power, which is the order of the group, that means you're raising it to its own order and then to a further power as well. So it's going to hit the identity. Okay. So this is a consequence.
Yeah.
If you take any of the rotations, if it's a n-sided polygon, take any of the rotations, do it n times, it has to be the identity.
Yeah.
Yeah. That's an example of that. Yeah. Yeah. So consequence, yeah. Consequence. So, but we do want to mess around with the indices as well. So that implies that this one, G to the R to the power P is equal to E. Now that tells us, i.e. the order of G to the R divides P. If you have a group element raised to a certain power, that gives you the identity element. In the order of the original element, it must be a divisor of that power. So what does that tell us about the order of G to the R? Well, if it divides P, it can only be one of two things, 1 or P. Yeah. If we know it's P, then finally we'll have proved the lemma for this. Yeah. Remember, the lemma says the group has an element of order P. So that's what we're gunning for. So we want to prove that G to the R has order P. Now we know it's only has order 1 or P. So we need a proof by contradiction, probably. Proof by contradiction that G to the R is not the identity. It does not have order 1. If it had order 1, then G to the power R would be the identity. So assume that that's the case. Yeah, and then let's go back to our G. Consider G, and G is equal to G to the power 1. 1 we have as this represented in this interesting way. G to the SP plus T to the R. So that's 1 there, but expressed in an interesting way. S times P plus T times R. Yeah. And that we can split up using rules of indices. So we're using these all over the place. G to the SP times G to the TR. And that we are going to split up as G to the P to the S. But now you see, we just assumed that G to the R was the identity. So this one will write as G to the R to the T. But we've just assumed that G to the R is the identity. So this will drop. This is just the identity raised to the power of T. This is the identity. So this goes to G to the P to the S. Where is G to the P? We know something about G to the P. Look up the page. G to the P is in H. Yeah. If G to the P is in H, and you raise it to a certain power, it means you're still in H. But what's the problem with that?
G is not in H.
G is not in H. So we've just contradicted ourselves.
Yeah.
Okay? Contradicts what we know. So either everything's collapsing around us, or we made a little mistake along the way. The mistake we made along the way was here. G to the R was equal to. So G to the R is not equal to E. Okay, remember, we knew G was not in H. We knew that was the case because the coset GH was an element of order P. So it wasn't the identity. So this G to the R is not the identity. So it doesn't have order 1. So P is the only possibility remaining. G to the R has order. So it's the element that the lemma was claiming existed. And here we proved it exists, because here it is. Which finally proves the lemma in this case. Finally proves the lemma. For this case. And what you just want to appreciate or just want to make sure is that, you know, we've proved the lemma in all cases. Well, sorry, so therefore G has an element, G has an element of order P. It has an element of order P in all cases. So it's now this group G was a group of order n, and we proved that it had an element of order P using the truth of the earlier truth of smaller groups. So therefore, now using the principle of induction, we can assume it's true for groups of any size. By induction, for induction, the lemma is true for groups of any size. Finite abelian groups of any size. Finite abelian groups of any size. Okay. So the lemma is proved. And just like now we encountered many kind of cases and splitting there. So you just want to be sure you can see that we covered all the bases. Okay. Prove the base case n equals 1. Made the induction assumption. Separated off an easy case of boring groups, which don't have any intermediate subgroups. They're cyclic. The P must be the order of the element of the generator, so the lemma is true for those. And then this kind of the hardest case is where there is an intermediate group. And using things from number theory, P divided it, or the factor group. And those two groups are both smaller groups. The induction assumption applies to both. In case of H, you straight away get an element of order. Because the induction assumption applies to H, H is an element of order P, and that is also simultaneously sitting inside G. H is a subset of G. The slightly more difficult case was the factor group. Factor group is a smaller group than G. Therefore, by induction, it has an element of P, but we're outside the context of G now. We're now talking about cosets of H in G. But there is an element of G appeared, this element, little g here. It's not the one that has order P, but something related to it does, this power of it, e to the r. And just R was the, R was the size, R was the size of it. Okay. Okay, that's good. So it's a good thing I didn't try and blast through that in the last 10 minutes yesterday, because I wanted to give it a good treatment. Okay, so there's a little tiny one paragraph lemma coming next, and then a more substantial one, 13.8. Two more substantial, 13.8 and 13.9, that will get us to this group. So we'll tackle those next week. Okay.